It begins not with a bang but with a profound silence. Listen closely to the stillness of space and you can almost hear it, a quiet, persistent whisper. It is the sound of a new era beginning, the murmur of blueprints being unfurled and engines coming to life. This is the echo of a new space race, but it is not the one we remember from our history books. It has a different tone, a different purpose, and a vastly different set of rules. The race of the 1960s was loud, a direct confrontation fueled by the tension of a Cold War. It was a sprint between two superpowers, the United States and the Soviet Union, driven by political pride and ideological rivalry. The goal was to prove which system was superior, which nation had the technological and intellectual might to conquer the heavens. The moon landing was its breathtaking finale, a moment of victory symbolized by a flag planted in lunar dust. That race was about beating the other side. This new race is different. It is not about ideology, it is about existence. The driving force is no longer just political competition, but a shared global understanding of our own fragility. We look at our home planet and see its finite resources, its changing climate, and the challenges of supporting a growing population. The motivation now is survival expansion and the long-term continuation of the human story. It is a race less against each other and more against time, a collective effort to build a safety net for our species. The players have changed too. The field is no longer a simple duel. New national flags are rising, with China building its own space station and planning missions to the moon's South Pole, and India demonstrating incredible ingenuity with cost-effective missions to Mars and beyond. But the most significant change is the arrival of private industry. This is no longer the exclusive domain of governments. Visionary companies like SpaceX and Blue Origin are not just building rockets for hire, they are driving the pace. With reusable rockets that land themselves and ambitious plans for city-sized starships, these private pioneers are fundamentally changing what is possible, often moving faster and with more audacity than their government counterparts. This is the central theme of our new beginning. The last race was about planting flags. This race is about building a home. The goal is not just to visit, but to stay. We are talking about lunar bases that serve as refueling stations, mining operations on asteroids to gather precious resources, and a genuine, sustained human presence beyond the blue cradle of Earth. This is not just another chapter in human exploration. This is the prologue to a new book, entirely the first steps in our transition from a species that lives on one world to a species that lives among the stars. The whisper we hear is the sound of that journey beginning. For decades, human exploration of the moon was defined by the Apollo missions, quick, daring visits to plant a flag and gather stones. It was a race, a demonstration of capability, and an incredible achievement. But the goal was always to visit. Now the paradigm has shifted entirely. The new objective is not just to visit the moon, but to stay. This ambition changes everything, reframing the moon, not as a final destination, but as a critical piece of infrastructure, a proving ground for the technologies and a strategic way station for the long journey into the solar system. So why the moon? Why return after all this time? The answer is strategy. The moon is in essence a launch pad. Here. The single greatest obstacle to human exploration of space is Earth's powerful gravity. To escape our own planet, we must build truly colossal rockets burning millions of pounds of propellant just to reach low Earth orbit. It is an enormous and expensive effort. The moon, however, is a much smaller world with only about 1/6 of Earth's gravity. Leaving the moon's surface requires dramatically less energy and far less fuel. This low gravity makes the moon the perfect port for deep space. Instead of launching a massive, fully fueled Mars mission directly from the bottom of Earth's deep gravity well, we can launch the components to the moon. We can assemble and crucially fuel them there. A mission leaving from the moon for Mars begins its journey with an incredible advantage, saving time, money, and mass. This strategy only works if the moon itself can provide the resources, which is why the location of a future base is so critical. The new lunar focus is not on the flat equatorial plains of the Apollo missions, but on the rugged, cratered terrain of the lunar South Pole. This region offers a unique combination of resources found nowhere else. On the high rims of certain craters, sunlight is nearly constant. These peaks of eternal light are ideal locations for solar panels, providing a steady, uninterrupted supply of energy. But the true treasure lies in the nearby shadows. At the bottom of deep craters near the pole, there are areas that have not seen sunlight in billions of years. These permanently shadowed regions are some of the coldest places in the entire solar system. They have acted as cosmic cold traps, perfectly preserving a resource that will define the future of space exploration water ice. This brings us to the most vital concept for long-term survival in situ resource utilization, or ISRU. This is a simple idea with profound consequences living off the land. Instead of shipping everything we need from Earth at an astronomical cost, we will learn to harvest and use the materials already on the moon. The water ice is the primary target. First, astronauts can melt it for drinking water. Second, they can use it to grow food. But its most powerful use comes from a simple process called electrolysis. By running an electric current generated by the solar panels through the water, it splits the molecules into their two component parts, hydrogen and oxygen. This is a game changer. The oxygen is obviously breathable air for the habitat. When the hydrogen and oxygen are chilled into liquids, they become the most potent and efficient chemical rocket propellant known. The moon's ice-filled craters are not just a water source, they are quite literally a future fuel depot. The water ice isn't the only resource. The very soil of the moon, the fine dusty layer called regolith, is also a valuable asset. The regolith is rich in oxides, meaning its chemical structure contains vast amounts of trapped oxygen. By heating the regolith in a reactor, this oxygen can be baked out and captured, providing another source of air to breathe. Furthermore, the regolith itself is the perfect building material. Rather than shipping heavy metal habitat modules from Earth, we can use the regolith as the raw material for 3D printing. Large-scale 3D printers using focused sunlight or lasers to melt and fuse the regolith, a process called sintering, can construct landing pads, radiation shields, roads, and even the habitats themselves. Before we can confidently send humans on a 2-year journey to Mars, we must know that our systems work. The moon is the perfect place to test them. It is our proving ground. It is close by, only a 3-day trip away. If a critical life support system, a water recycler, or a regolith 3D printer breaks down on the moon, a rescue or resupply mission from Earth is feasible. If the same thing happens on Mars, the crew is on its own 6 months away from any possible help. On the moon, we will test the habitat modules, the rovers, the power systems, and the ISRU equipment, hardening them for the far more dangerous and autonomous mission to Mars. But the most important systems we must test are the human ones. The moon will be a crucial testbed for human psychology. What is the long-term mental and emotional effect of living in a small enclosed habitat in a world that is utterly silent and sterile? How will astronauts cope with the intense isolation not just from other people but from all life? The moon is a grey, airless world. The only connection to home is the constant presence of Earth hanging in the black sky, a beautiful, fragile blue and white marble. Witnessing this overview effect for months on end is a profound psychological experience, one we must understand before sending a crew so far out that Earth itself becomes just another small point of light in the sky. This is the ultimate vision. The moon is not the finish line, it is the starting block. It will become our first true off-world centre, a bustling port of call, a scientific laboratory, and a training ground. From the far side of the moon, shielded from the radio noise of our planet radio telescopes, we'll listen to the deepest secrets of the cosmos. From the South Pole, fueled by lunar water and built from lunar soil, the first human missions to Mars will ignite their engines. The moon is the bridge from being a species that visits space to becoming a species that lives and moves within it. If the moon was a test of our ability to reach Mars, is the true test of our ability to stay. The two destinations are often spoken of in the same breath, but they represent entirely different levels of commitment and challenge. Going to the moon is like taking a 3-day trip across a local bay. If the weather turns bad or the engine sputters, you can turn around and be home by dinner. The proximity of Earth is a constant comfort, a massive, beautiful blue and white shield hanging in the black sky. Mars is not like that. Mars is the equivalent of getting on a ship in the 17th century to cross the Atlantic, knowing that the journey itself will take 6 long months, and that once you're in the middle of that ocean, there is no quick return. This is the fundamental difference that changes everything. The journey to Mars is a commitment of time, energy, and orbital mechanics. You cannot simply go whenever you want, and you cannot come back when you're scared. The planets must be in the correct alignment, a window that opens only once every 26 months. Once you ignite your engines and leave Earth's orbit, you are locked into a trajectory. A catastrophic failure halfway to Mars does not mean a quick U-turn. It means a long, complex, and desperate maneuver just to get back into an orbit that might eventually bring you home months or years later. The 6-month voyage is not a commute. It is an endurance test in itself, a passage through deep seas where the crew is isolated and completely on their own. And then if you survive the journey, you arrive at the destination. And the destination is trying actively to kill you every second of every day. The Martian environment is not just harsh, it is fundamentally incompatible with Earth-based life. The dangers are pervasive and they begin with the things you cannot even see. First, there is the radiation. Earth is a safe harbour. We live our lives protected by a powerful global magnetic field, a magnetosphere, that deflects video. It deflects the constant stream of high-energy particles from the sun, the solar wind, and the far more dangerous galactic cosmic rays or GCRs, which are particles accelerated to near light speed by distant supernovae. Mars lost its magnetic field billions of years ago. Its core cooled and its protective shield vanished. Today, the surface of Mars is constantly scoured by this radiation. For a human, this is not a vague long-term risk. It is a daily accumulating dose of damage. It shreds DNA, increases cancer risk dramatically, and can even impact cognitive function, causing what some scientists call space brain. There is no atmosphere thick enough to stop it. There is no magnetic field to deflect it. It is a constant invisible rain of destruction. Second, there is the temperature. The user-friendly colder than Antarctica is an understatement. Antarctica at its most brutal might reach -80 or -90 degrees Celsius. Mars can easily match that, but its average temperature across the planet is -63 degrees Celsius. It can be warmer at the equator during the day, perhaps reaching a comfortable 20 degrees Celsius or 70 degrees Fahrenheit, but at night the temperature plummets by over 100 degrees easily, reaching -73 degrees Celsius. This constant extreme thermal cycling is not just uncomfortable, it is a nightmare for engineering. Metals become brittle, seals crack, and lubricants freeze solid. Keeping a habitat warm does not just mean running a heater, it means fighting a constant losing battle against the frozen vacuum outside, requiring an enormous and uninterrupted supply of power. Third, there is the pressure or the lack of it. The Martian atmosphere is incredibly thin, less than 1% of Earth's pressure at sea level. This is functionally a vacuum. If you were to step outside without a specialized, fully pressurized suit, the experience would be gruesome and brief. The low pressure would cause the fluids in your body, the water in your skin, your tongue, your eyes, and ultimately your blood to boil. This is not boiling from heat, but boiling from the absence of pressure holding the liquid in. You would be dead in seconds. The air itself is also toxic. It is about 95% carbon dioxide, gas we breathe out as waste. These three challenges, radiation, temperature, and pressure, mean that humans can never ever interact with Mars directly. They must always be inside a machine, whether that machine is a habitat, a rover, or a suit. But the environment has one more brutal trick: the ground itself. The fine red dust that covers the entire planet is not like sand on an Earth beach, worn smooth by the water and time. Martian regolith or soil is a field of microscopic jagged shards. It is pulverized volcanic rock that has been ground down by wind, but never softened by water. Like tiny bits of glass, it will get into everything. It will clog air filters, tear up the joints in spacesuits, abrade seals on airlocks, and destroy machinery. And it is not just sharp, it is toxic. We have learned from our robotic rovers that Martian soil is full of perchlorates, a class of chemical that is highly toxic to the human thyroid gland. If astronauts track this fine toxic, sharp dust into their habitat on their boots and suits, which is inevitable, it will become airborne. They will breathe it in. This dust is not just a nuisance, it is a long-term medical and mechanical hazard that could cripple a mission from the inside out. Given these conditions, the challenge of building a home on Mars is enormous. You cannot simply land a prefabricated house and move in. To survive the big three: radiation, temperature, and pressure, you must be shielded. The most logical solution is to go underground. Astronauts will not be colonists, they will be miners. They must use the planet itself as their shield. The best defense against radiation is mass. By burying a habitat under 2 or 3 meters of Martian regolith, you can effectively block most of the deadly cosmic rays and stabilize the internal temperature. Early missions will likely involve landing heavy-duty construction robots, first bulldozers and tunnelers, that will spend months or years preparing a buried shelter before the humans even arrive. An even better solution would be to find natural lava tubes, which are massive underground caves left behind by ancient volcanic activity. These tubes are already there, offering pre-built radiation-shielded tunnels that are potentially large enough to house an entire town. If you cannot build down, you must build over. Surface habitats will need to be covered piled high with thick layers of soil or perhaps shielded by walls made of ice water. Ice, which is plentiful at the poles and underground, is surprisingly effective at blocking radiation. Either way, the era of living in thin-skinned modules on the surface is over. Mars demands we become a subterranean species, and yet the greatest challenge may not be the environment, it may be the human mind. The physical isolation of Mars is unlike anything humanity has ever experienced. From the surface of Mars, Earth is not a big blue marble. It is a pale blue dot, just another bright point of light in the sky, indistinguishable from a star to the naked eye. This psychological distance is profound. There is no looking home for comfort. You're utterly, completely, and visibly alone. The crew of 4, 6, or 8 people in that small habitat will be the only humans they see for years. There is no escape. There is no going for a walk to clear your head. There is no new person to talk to. If conflicts arise, they must be managed because the survival of everyone depends on the crew functioning as a perfect unit. This sense of isolation is magnified to an extreme degree by the communication delay. Mars is so far away that light itself takes time to travel. Depending on the planet's orbits, a radio signal takes between 4 and 24 minutes to travel one way. This means there is no such thing as a phone call. There is no real-time conversation. Imagine an emergency. An alarm sounds in the habitat. The commander cannot call mission control and ask, "What do we do?" They must send a message, a detailed description of the problem, and then wait. They might have to wait 40 minutes, 20 minutes there, 20 minutes back for a reply. By then they could all be dead. The Martian crew must be totally autonomous. They must be the mechanic, the doctor, the scientist, and the psychologist all rolled into one. They must be able-bodied to solve every single problem on their own, with only a delayed email support from the best minds on Earth. This delay also fundamentally severs the social connection to home. You cannot call your spouse or your children. You can only send them a video message and get one back perhaps the next day. The loneliness will be staggering. To survive this, a Mars colony must be a perfect closed system. It must be completely self-sufficient. There are no resupply missions. The Amazon delivery time is 6 months, and that is only if the launch window is open. This means you must make everything yourself. First, food. You must become farmers. Huge sections of the habitat will be dedicated to growing food, likely in hydroponic water-based or aeroponic mist-based bays under bright LED lights. These farms will grow potatoes, soybeans, wheat, and leafy greens, everything needed for a complete sustainable diet. This green space will also be crucial for mental health, a reminder of life on a dead world. Second, you must recycle everything. Everything. The International Space Station already does this, but a Mars colony must be perfect. Every drop of water from human breath, sweat, and urine must be collected, purified, and returned to the drinking supply. Every molecule of carbon dioxide the crew exhales must be scrubbed from the air and processed. That carbon can be used to feed plants or, using chemical reactors, be combined with hydrogen from water ice to create methane for rocket fuel. The oxygen can be reclaimed for breathing. This is the ultimate zero-waste society, not for philosophy, but for survival. Finally, none of this works without energy. Solar panels are a poor choice on Mars. The planet is farther from the sun, so the sunlight is weaker. More importantly, Mars is prone to planet-encircling dust storms that can last for months, blocking almost all light. A solar-powered base would die. The only reliable solution is nuclear power. This means small compact nuclear fission reactors like the Keeler power system prototyped by NASA. These are small, safe, and can be buried next to the habitat, providing a steady, powerful, and reliable source of electricity for decades regardless of the weather, the dust, or the time of day. This energy is life. It runs the heaters, the air recyclers, the water purifiers, and the farm. This is the true meaning of the Mars test. The Moon was a test of our rockets and our computers. Mars is a test of our biology, our psychology, and our engineering at a systemic level. It forces us to create a miniature, artificial, and perfect version of Earth's own biosphere. If we can succeed, if we can learn to live, thrive, and build a self-sustaining home on a frozen, irradiated, toxic, and distant world, it proves something profound. It proves that life from Earth is not bound to this one planet. It proves that we are resilient, adaptable, and clever enough to survive anywhere. Solving the problems of Mars, perfect recycling, compact nuclear energy, advanced agriculture will give us the very tools we need to solve our problems back on Earth. Let your mind drift, let it settle and think about our small blue world. We look up at the night sky and we see lights. We see the steady reddish glow of Mars, we see the brilliant pinpoint of Jupiter, we see the faint distant light of Saturn. On our maps of the solar system, they look so close, just neighbours in our own cosmic backyard, but the universe is playing a quiet, subtle trick on us. The Great Barrier isn't just the distance, the millions and millions of miles. We can measure that distance, we can understand it. The true barrier, the one that keeps us tied to our home, is time. The way we travel in space even now is ancient. It is based on fire. We use chemical rockets, we mix a fuel, and we mix an oxidizer, and we create a controlled, violent explosion. It is a magnificent, powerful push. For a few short minutes, the engine roars, fighting gravity, lifting the tiny capsule up through the atmosphere and into the quiet of space. And then the fire goes out, the engine falls silent. For the rest of the journey, whether it is 6 months, or 8 months to Mars, or 6 years to Jupiter, the spacecraft is just coasting. It's drifting. It's like standing on the shore of a vast dark ocean and throwing a stone as hard as you can. You give it one powerful throw and then you just wait. You watch it sail, following the invisible curves of gravity, hoping it lands where you aimed. This is the tyranny of time, and this drifting is dangerous, not just boring, but dangerous. Out there in the deep dark, there is no atmosphere to protect us. There is no magnetic field, no warm blanket like the one our Earth wraps around us. There is only the void, and the void is full of radiation. There is the solar wind, a constant stream of particles from our own sun, and there are cosmic rays, tiny invisible bullets travelling at nearly the speed of light shot from exploding stars millions of years ago, halfway across the galaxy. They pass right through the thin metal skin of the ship. The longer you're out there, the longer you drift. The more of these tiny bullets pass through you, the damage it just accumulates. A 6-month trip to Mars is a long time to be in that environment. A 3-year round trip is a very long time. If we're ever going to truly explore to live in our solar system, we cannot just be coasters. We cannot just be stone throwers. We must build a ship that doesn't just push and drift. We must build a ship that can sail. We need a better engine. The first great idea. The next logical step is to harness the power locked inside the atom. It's an idea we've had for decades, waiting for us to be brave enough to use it. It is called nuclear thermal. It still uses a familiar friend, hydrogen. Simple, light, abundant hydrogen. In our old chemical rockets, we burn the hydrogen. We mix it with oxygen and make an explosion. In a nuclear thermal engine, we do something far more powerful. We don't burn it, we heat it. Imagine deep inside the engine there is a small protected core, a nuclear reactor, but not one that makes electricity. This one is designed to make one thing pure, raw heat. Inside this core, heavy atoms like uranium are encouraged to split apart. This is called fission, and when they split, they release an incredible and unbelievable amount of energy as heat. Now we take our cold liquid hydrogen, and we pump it right through the heart of that tiny raging sun. The hydrogen doesn't burn, it doesn't explode, it just boils. In less than a second, it flashes from a super cold liquid to a gas heated to thousands and thousands of degrees. It expands with furious power and roars out of the nozzle at speeds our chemical rockets simply cannot match. The gas mileage. The efficiency of this engine is doubled. It is 2 or even 3 times better than the best chemical rocket we can build. What does this mean? It means that trip to Mars, that 8-month drift, is cut in half. 4 months, maybe 3. The time spent in the dark, the time spent soaking in that invisible radiation, is cut in half. Journeys that seem almost impossible, like sending humans to the moons of Jupiter, suddenly become possible. Difficult, but possible. This isn't a dream. This is science, just waiting to be built. It is the first key to unlocking the door, but fission-splitting atoms is only the first step. It's a faster way to sail. The ultimate dream is to build a star. We are dreaming of fusion. Fission, remember, is about splitting heavy things apart. Fusion is about joining light things together. This is the secret of our own sun. This is the engine that powers the entire solar system. Every second, deep in the crushing gravity of the sun's core, it takes the lightest thing, hydrogen, and under pressure and heat we can barely imagine, it fuses it. It squeezes 2 hydrogen atoms together so hard that they become one. They become helium. In that tiny magical moment of joining, a little bit of their mass, just a tiny, tiny fraction, vanishes. It doesn't disappear. It is reborn as pure energy. You know the name of this: magic E equals mc squared. Energy equals mass times the speed of light squared. It is the universe's most generous exchange rate. To build a fusion engine is to build a star in a magnetic bottle. It is perhaps the most difficult engineering challenge humanity has ever faced, to create a plasma, a gas hotter than the surface of the sun, and to hold it to contain it using invisible fields of magnetism so that it doesn't melt the very ship it's trying to push. We are trying on Earth right now, we are trying to build them to create clean energy. But if we can do it, if we can build one and make it small enough and safe enough to put on a spaceship, well, everything changes. The efficiency isn't just double. It's not 10 times better. It is hundreds or thousands of times better. The fuel types of hydrogen can be found in the oceans of Earth, in the ice of the Moon, in the atmospheres of the giant planets. A fusion rocket wouldn't just push and coast. A fusion rocket could accelerate. It could push gently but constantly for the entire first half of the journey, building speed hour after hour, day after day. And then halfway there it could turn around and it could brake using its own engine for the entire second half of the journey. That trip to Mars, not months, weeks. That trip to Jupiter, not years, months. The entire solar system, from the hot-baked plains of Mercury to the cold, distant twilight of Pluto, and the Kuiper belt would be open to us. It would be our neighborhood. And for the very first time, those other lights, the ones that are not planets, the distant patient stars, they would stop being just points of light, they would stop being just poetry. They would become destinations. There are other dreams too. Quieter dreams, like ion engines. We use these already. They are real. Our deep space probes, the ones that travel to asteroids or to Mercury, they use them. An ion engine doesn't roar, it whispers. It takes electricity perhaps from giant delicate solar panels, and it uses that power to gently push out single atoms ions. The thrust is tiny. It's like the pressure of a single piece of paper resting on the palm of your hand. But in the perfect vacuum of space where there is no air, no friction, that tiny, relentless whisper adds up. It pushes every minute, every hour, every day for years. It is the ultimate marathon runner. Patiently, steadily building up speed faster and faster than any chemical rocket could ever go. And there are hybrids, mixtures of these ideas, like Vasimar, a plasma rocket. It uses electricity and magnetic fields and radio waves to heat a gas to create a controlled plume of lightning, an engine that can be efficient and powerful. All of these ideas, the thermal, the fusion, the ion, the plasma, they are all chasing the same ghost. They're all trying to defeat time. They are all clever, beautiful human ways to turn years into months, to turn months into weeks. They are the keys to breaking the chains of our old fiery technology, to unlocking the map of our solar system, and to finally stepping out into the great, wonderful open dark. And as you drift off to sleep, just imagine that, a quiet ship sailing on a whisper, or pushed by a tiny captured star gliding silently past the rings of Saturn on its way out. Mars is the ultimate final exam. If we can make a life there, we can make a life anywhere. For the whole of human history, wealth has been defined by what we could dig out of the ground. We drilled for oil, mined for coal, and excavated for diamonds. Our economies, our technology, and even our conflicts were based on the idea that resources were scarce and located beneath our feet. The 21st century is forcing a fundamental paradigm shift. The greatest concentration of materials essential for our species' future is not underground, it is overhead. We are beginning to understand that the asteroid belt, the vast collection of debris orbiting between Mars and Jupiter, is not just a navigational hazard. It is a resource belt of unimaginable wealth. This isn't just about rocks. It's about the raw leftover building blocks of our solar system preserved in the cold vacuum of space for billions of years. The initial allure of this new gold rush is obvious: precious metals. When the Earth was young and molten gravity did a very inconvenient thing. It pulled all the heavy elements, iron, nickel, cobalt, and the platinum group metals like platinum, iridium, and palladium down to the center, forming the planet's core. These elements are now thousands of kilometers beneath our feet, almost completely inaccessible. Asteroids are different. Many are the unchanged remnants of the solar system's birth. They never got large enough to melt and differentiate meaning. Their precious metals are not locked away in a core. They are scattered throughout the asteroid, often in concentrations vastly higher than anything found in Earth's crust. Furthermore, we have identified specific M-type metallic asteroids. These objects are believed to be the exposed, shattered cores of ancient planetesimals, or small developing planets that were destroyed by impacts long ago. They are quite literally giant floating mountains of almost pure iron and nickel, laced with quantities of platinum group metals that defy conventional imagination. A single small metallic asteroid, perhaps only 1 kilometer wide, could easily contain more platinum than has ever been mined in all of human history. The monetary value is not measured in billions, but in trillions. But here is the most important concept of the new space economy: the gold rush metaphor is misleading. The old model was find gold, haul it back to Earth, and become rich. This model fails in space. The real value of asteroid materials is not bringing them back to Earth. First, returning massive payloads to Earth's surface is incredibly difficult and expensive. You have to fight Earth's massive gravity well every step of the way, requiring enormous amounts of fuel just to slow down and land safely. Second, if you did manage to bring back thousands of tons of platinum, you wouldn't become rich. You would instantly crash the global commodities market, making your own cargo nearly worthless. The true value is using the materials on site. In space, the most valuable resource is anything you don't have to launch from Earth. The cost of space exploration is defined by the tyranny of the rocket equation. To go anywhere, you must carry fuel. But that fuel has mass, which requires more fuel to launch it. It's a vicious cycle. Launching 1 kilogram of anything from Earth's surface to orbit costs thousands of dollars. This is where the other type of asteroid becomes critical, the C-type, or carbonaceous asteroids. These are not rich in metal, but they are rich in water ice. Water is the gold of the high frontier. In space, water has two primary uses. Life support astronauts can drink it and use it to grow food. Rocket fuel. Using electricity from solar panels, water H2O can be easily split into its component parts, hydrogen and oxygen. Liquid hydrogen and liquid oxygen are the most powerful chemical rocket propellant we know. An asteroid mining operation that harvests water ice is not a mine. It is a gas station in the middle of the solar system. A spaceship traveling from Earth to Mars could launch with relatively empty tanks, making it much lighter and cheaper. It would then stop at the asteroid gas station to refuel for the rest of its journey. This single concept, in situ resource utilization (SRU), breaks the rocket equation and opens up the entire solar system. Once you have energy, solar panels, fuel from water ice and structural materials, iron, nickel and aluminum from metallic asteroids, the next logical step is construction. Currently, every object we put in space, from a small satellite to the International Space Station, must be built on Earth. It must be engineered to withstand the bone-jarring violence of a rocket launch, and it must be meticulously folded to fit inside the narrow cone or fairing at the top of a rocket. Asteroid resources change this completely. We can stop shipping flat-pack components and start manufacturing in space. With 3D printers and automated assembly arms, we can use the processed asteroid metals as raw feedstock. We could begin to assemble massive structures that would be impossible to launch from Earth. This includes giant satellites with enormous solar arrays or antennas far larger than any current design. Orbital factories, dedicated facilities for processing materials in the unique vacuum and microgravity environment. Deep space vessels. We could build massive shielded ships in orbit. These ships born in space would never need to land on a planet. They would be constructed from asteroid metal fueled by asteroid water and capable of taking crews to Jupiter, Saturn and beyond. This vision is profound, but the engineering hurdles are unlike anything humanity has ever faced. Mining on Earth is difficult. Mining in a zero-gravity vacuum is a new frontier of physics and engineering. First, there is the challenge of mining in microgravity. On Earth, gravity holds your truck, your tools, and the rocket itself in place. In space, an asteroid has almost no gravity. If a robot tries to land on it, it will just bounce off. If it tries to push a drill into the asteroid's surface, Newton's third law states that the robot will be pushed backward into space. To mine, you must first anchor your equipment. This might involve firing harpoon-like cables into the asteroid or using powerful grippers to grab onto the surface. Furthermore, any mining action, drilling, grinding or scooping will kick up a cloud of dust. In a vacuum with no gravity, this dust will not settle. It will float indefinitely, clogging machinery, coating solar panels and creating a hazard for any nearby spacecraft. Second, there is the challenge of processing in a vacuum. On Earth, we use techniques like smelting, which often rely on oxygen in the atmosphere, and use gravity to separate heavy molten metals from lighter slag. These methods don't work in space. We must invent new space metallurgy. One promising idea is carbonyl processing. For a metal-rich asteroid, you could expose the crushed rock to carbon monoxide gas. The gas selectively reacts with metals like nickel and iron, forming a new gas, a carbonyl. This gas is then siphoned off, and when heated, the pure metal deposits out, leaving the rock and impurities behind. Other methods might use massive lightweight mirrors to focus pure sunlight, melting the ore in a solar furnace. If we can master these challenges, anchoring, mining and processing, the long-term vision becomes truly transformative. We would move beyond simply exploiting resources and toward becoming a truly spacefaring species. The ultimate goal is not just to mine the asteroids, but to inhabit them. Many M-type asteroids are giant solid chunks of metal and rock. A mature space economy could begin to hollow out these asteroids, mining the valuable materials from the inside out. This would leave a massive empty cavern protected by an outer shell of rock and metal meters or even kilometers thick. This shell provides something priceless shielding. One of the greatest dangers to life in space is constant radiation from cosmic rays and solar flares. A thin-walled space station offers little protection, but the thick natural shell of an asteroid provides near-perfect shielding, making the interior a safe haven for life. But the interior is still in zero gravity, which is terrible for human health. The solution proposed by physicist Gerard O'Neill is simple: spin the asteroid. By spinning the hollowed-out cylinder, the force of centripetal acceleration, often called centrifugal force, would push everything toward the inner surface. If you spin it at the correct speed, you can perfectly simulate the 1G gravity of Earth. This is the O'Neill cylinder model. Humans would not live on the surface of this new world, they would live inside it. The ground would be the curved inner wall. People could build towns, plant forests, and create rivers all on the inner surface of the spinning, hollowed-out worldlet. The very resources we came to mine, the iron and nickel, would become the foundations of a new, permanent home in space. We would be living inside the resource, self-sufficient and safe from the dangers of the cosmos. This is the rule, and it is the most important rule of deep space exploration. The machines always go first. This is not a suggestion. It is a fundamental law of survival. Before we send fragile human bodies full of needs and fears into the most hostile environments in the solar system, we send our toughest representatives. These are the rovers, the probes and the landers. They are the silent pioneers, the scouts and the advanced team. The reason is simple. A robot does not need to breathe. It operates perfectly in the thin, unbreathable atmosphere of Mars, which is 95% carbon dioxide. It functions just as well in the complete vacuum of the Moon. A robot does not need life support, which is the single heaviest, most complex and most failure-prone system we must design for human spaceflight. A robot does not feel fear. The crushing cold of a Martian night, which can fall to -100 degrees Celsius, is just a number on a sensor. It does not worry about the constant invisible rain of cosmic radiation that damages living cells. It can perform the same repetitive, boring task, like digging in the soil or analysing a rock for 10 years straight, without getting distracted, without making a careless mistake, and without feeling lonely. And perhaps most importantly, a robot does not get homesick. The journey to Mars takes 6 to 9 months one way. A robot can make that journey, land, and then wait patiently for 2 years or 5 years or 10 years for the humans to finally arrive. It does not suffer from psychological stress, isolation, or depression. The immense time delay in communication is a major challenge. When a robot on Mars sends a signal to Earth, it takes on average 20 minutes for that signal to reach us. It takes another 20 minutes for our reply to travel back. This 40-minute lag makes direct remote control impossible. For a robot, this delay is an operational problem to be solved. For a human trying to have a real-time conversation with their family, this delay would be a form of psychological torture. Because of these advantages, our machines have been steadily evolving. They began as simple scouts. The first rovers like Sojourner were small, like microwave ovens on wheels, just proving we could drive on another planet. Then came Spirit and Opportunity, true robotic geologists that travelled for miles and lasted for years, fundamentally changing our understanding of water on the ancient Mars. Now we have the next generation. The Perseverance rover is a mobile astrobiology laboratory. It is not just looking for signs of past life, it is a vital part of a long-term plan. It is actively drilling rock samples, sealing them in tubes and leaving them on the surface for a future mission to pick up and return to Earth. It is the first link in a logistical chain. Beside it, the small helicopter named Ingenuity proved that we could fly in an atmosphere that is only 1% as dense as Earth's. It completely changed our perspective. We are no longer limited to just roving, we can now fly. But this is still just the scouting phase. The next evolution is the most important, the autonomous builder. The vision for the first human base on Mars does not begin with a human landing. It begins 10 years earlier with the landing of an automated fleet. These are the construction crews. Imagine several large landers touching down in a pre-selected area. The first robots to deploy will be the power technicians. Their only job is to provide energy. They will unroll vast, flexible solar panels, thin sheets that are durable and designed to shed the Martian dust. They will cover an area the size of a football field, soaking up the weak sunlight. Other robots might be tasked with deploying a small nuclear reactor, perhaps a system like the kilopower reactor, burying it in a pre-dug pit to shield the future habitat from its radiation. This will provide constant, reliable power day and night. Once the lights are on, the second group of robots gets to work the miners. We know there is vast frozen water ice buried just beneath the Martian surface. Specialized robots will scrape away the topsoil of the regolith and begin to drill or heat the ground. They will warm this icy soil, capture the water vapor that is released, and condense it into liquid water. This water is collected and stored in large insulated tanks. This water is everything. It is for drinking for growing plants, and when split into its components of hydrogen and oxygen, it is breathable air and rocket fuel for the journey home. With power and the water secured, the main construction begins. We cannot ship a fully built base from Earth. It is simply too heavy and too expensive. Instead, we ship a 3D printer. This will be a large mobile robotic arm, or perhaps a gantry. Its ink will be the Martian soil itself. The robot will scoop up the red regolith, mix it with a special binding agent, a polymer we bring from Earth, and begin to print layer by layer. It will print landing pads first, so the human ships don't blast the base with rocket exhaust. It will print garages to protect the rovers. It will print thick radiation shields. And finally, it will print the primary habitat, the shell that will protect the astronauts from the harsh environment. When the first humans finally arrive, they will not be landing in a desolate wasteland with nothing. They will be arriving at a pre-built base that is already powered, already stocked with water, and ready for them to move in, pressurize, and begin their work. This entire vision, this decade-long construction project, is impossible without the final, most crucial element, artificial intelligence, or AI. The machines cannot be simple remote-controlled toys. That 40-minute time delay makes it impossible. If a construction robot is about to make a critical error, or if a mining robot's drill gets stuck, we cannot fix it from Earth in time. The machine will be broken or the base will be ruined long before our stop of command even arrives. The robots must be autonomous. They must have brains. The AI's first job is self-diagnosis and repair. Each robot must be smart enough to know when it is sick. Its AI must constantly monitor all its own systems. If it detects that a wheel motor is drawing too much power, it must deduce why. Is the wheel stuck in soft sand? Is a bearing failing? The AI must then run thousands of simulations in its own processor. If I try turning the other wheels, can I get free? If I reduce power to this motor, can I still complete my task just more slowly? It must be able to solve its own problems. If a critical part breaks, the AI must be able to guide a smaller specialized repair bot to fix it, or at least stabilize the problem until humans can arrive. When the humans finally land, the AI's role shifts. It transforms from construction foreman to base operations manager. It becomes the central intelligence of the habitat, the ship's computer, from science fiction made real. This AI will manage the life support systems, constantly checking the mix of oxygen and nitrogen in the air. It will optimize the power grid, deciding where to send energy during peak demand. It will monitor supplies, automatically track food and water levels, and calculate how many days of resources the crew has left. It will be the crew's chief engineer, doctor, and operations expert all in one. It will also be their medical assistant. Sensors built into the astronauts' suits and sleeping quarters will constantly track their vital signs: heart rate, blood pressure, oxygen saturation, and most importantly, cumulative radiation exposure. The AI will be the first to know if an astronaut is getting sick, perhaps even before the astronaut feels any symptoms. It can recommend changes in diet, adjust exercise routines, or warn a crew member that they have reached their radiation limit for the month and must stay inside. In a true medical emergency with no specialist surgeon available, the AI would be the calm, steady voice guiding a non-expert crewmate through a complex procedure step by step. This leads to the most complex role for AI, the companion. Isolation on Mars will be the most profound isolation in human history. The crew will be a handful of people on an entire planet separated from their species by millions of miles of empty space. The psychological pressure will be immense. An AI could be a vital tool for mental health. It can be a person to talk to that is not one of your crewmates. It can be a non-judgmental ear, a partner for a game of chess, or an interface to all of Earth's music, movies, and literature. It could even be programmed to help mediate conflicts between crew members, offering objective solutions. This all leads to the final and most difficult philosophical question. As we make these machines smarter and more independent, how much autonomy do we really give them? We need the AI to be autonomous enough to save the mission if a life support system fails. But what does that mean? What if the AI, in managing a catastrophic failure, calculates that it can only save 3 of the 4 crew members? Does it make that choice? Who programmed that ethical decision? What if a robot builder programmed to be efficient decides that the habitat plan the humans sent from Earth is flawed? Does it have the authority to correct the human design and build what it thinks is better? We give a robot the autonomy to fix a broken wire. Do we give it the autonomy to override a direct command from a human astronaut if the AI believes that command is illogical or dangerous? These are not just technical problems, they are ethical ones. The silent pioneers we send ahead are not just tools, they are mirrors of our own intelligence. In designing their minds, we are forced to define the limits of our own control, our own trust and our own judgment long before the first human foot ever steps on the red sand. Even if you are listening to this in the dead of night, you can feel it. It is a memory stored in your skin, a warmth that anchors our entire concept of life. Our sun. It is the great glowing heart of our solar system, the engine of our world, the silent constant presence in our sky. It feels permanent. It feels reliable. It feels eternal. But in the quiet, patient halls of the cosmos, nothing is eternal. Not the mountains, not the oceans, and not the stars. We, in our brief, hurried flicker of awareness, have looked out into the vastness, and we have learned to read the stories of the stars. We see their births in swirling clouds of gas. We see their long, stable lives, and we see their deaths. And in seeing their deaths, we have read the future of our own star. This is not a guess. It is not a story we tell ourselves to feel small. It is a truth written in the fundamental laws of the universe. It is physics. The hard, inescapable truth is this: our sun will die. It's a process of unimaginable scale, slow, methodical, and inevitable. For billions of years, our star has been in a perfect, delicate balance. Deep in its core, it is a colossal furnace. It is taking hydrogen, the lightest and most simple element, and fusing it, crushing it together under immense pressure and heat to create helium. This process, nuclear fusion, releases a staggering amount of energy. That energy pushes outward, fighting back against the sun's own immense gravity, which is constantly trying to pull it inward. It is this balance, gravity pulling in, fusion pushing out, that has kept our star stable for all of human history and for long before. But this fuel, this vast ocean of hydrogen in the core, is not infinite. In about 5 billion years, the hydrogen fuel in the very center of the core will begin to run out. The furnace will sputter and the delicate balance will be broken. When the outward push of fusion falters, gravity will win. The core will begin to collapse in on itself, becoming denser and unimaginably hotter. This new intense heat will be so great that it will ignite the shell of hydrogen that surrounds the depleted core. This new furious burning will be far more intense than before. The sun's outer layers will begin to swell, pushed outward by this desperate final surge of energy. It will grow and grow and grow. The sun will expand, becoming larger than we can possibly imagine, swelling past the orbit of Mercury and then past the orbit of Venus. It will become a new kind of star, a red giant. Its color will change from the familiar, friendly yellow-white to a deep, menacing red. It will fill our sky, a crimson wall of fire. And our Earth, our small blue fragile home, will be directly in its path. The oceans will boil away first. The atmosphere will be stripped from the planet by the intense solar winds. The continents themselves will melt, turning our world into a sphere of molten slag. And then the expanding edge of the sun will reach us. The Earth will be consumed. It will be swallowed whole, vaporized, and become nothing more than a trace memory within the fiery atmosphere of its dying star. It will be an end of biblical proportions, an end written not in scripture, but in the mathematics of stellar evolution. This is the fate of our world. And what of the sun after this final terrible expansion? This red giant phase is just that, a phase. After perhaps 1 billion years, its new fuel sources will also run out. It will have nothing left to burn. Gravity, the great patient force of the cosmos, will win its final victory. The sun will no longer have the energy to support its own weight. The outer layers, the ones that consumed our world, will drift away into space, forming a vast, beautiful glowing cloud. We call these planetary nebulae. They are the ghosts of dead stars. And at the center, the core, the crushed, defeated heart of our sun, will remain. It will have compressed into an object about the size of the Earth, but containing the mass of half a sun. It will be a white dwarf. It will be a stellar ember glowing with leftover heat but creating no new energy. It will be a diamond in the sky made of crystallized carbon and oxygen, and it will simply cool and cool and cool for trillions of years until it becomes a black dwarf, a cold, dark, invisible cinder, wandering the final darkness of the universe utterly alone. This is the end. This is not prophecy, this is not mythology, this is not a worst-case scenario, this is physics. This is the timeline. It is as certain as gravity. It is as certain as time itself. And so we are faced with a profound, undeniable imperative. If our species, if consciousness, if the legacy of life that began in these oceans is to continue, we cannot stay here. If we stay, we end with it. And the only solution, the only path forward that allows for survival is to leave. We must become a species that does not keep all of its thoughts, all of its art, all of its memories in one single fragile basket. We must become a multi-planetary civilization. We must learn to live on other worlds. Perhaps Mars terraformed and given new life. Perhaps the moons of Jupiter or Saturn living beneath the ice in vast protected oceans. This will buy us time. This will give us a new foothold. But even that is only a temporary solution. Because when the sun becomes a red giant, this entire solar system will become uninhabitable. Mars will be scorched just as Earth will be. The outer moons will be blasted with radiation and heat. There is no refuge here. Therefore, the ultimate solution, the only one that ensures a future, is to become a multi-stellar species. We must find a way to cross the unimaginable gulfs of emptiness between the stars. We must take the spark of life that was born here and carry it to other suns, to new worlds orbiting new younger stars. This is not a choice, it is a requirement, but the death of the sun is 5 billion years away. It is an abstract, distant terror. It does not feel urgent, and yet there is a deeper motive, a more immediate reason why we must look to the stars. The universe has shown us that Earth is a cradle. It is the perfect, gentle, nurturing place where life could emerge, where consciousness could awaken. But a cradle is also by its very nature a trap. It has convinced us that we are safe, but we are not. We live on a rock covered in a thin, delicate film of water and gas floating in a cosmic shooting gallery. We are vulnerable. Think of the event that wiped out the dinosaurs. A single asteroid, a chance encounter, ended a reign of 150 million years in a single day of fire and darkness. It has happened before, and it will happen again. We scan the skies, we track the near-Earth objects, but we are one unseen rock away from oblivion. We are vulnerable to ourselves. We have built weapons of such power that we can extinguish our own civilization in an afternoon. We have built a global society so interconnected that a new deadly pandemic, far worse than any we have yet seen, could spread across the planet before we have time to react, silencing our world. We are vulnerable to the planet itself. Supervolcanoes like the one slumbering beneath Yellowstone could erupt with a force that plunges the globe into a volcanic winter, ending agriculture, ending civilization, and pushing humanity to the brink of extinction. We have all of our eggs in one basket, and the basket is fragile. The ultimate goal, then, is not exploration. It is not conquest. It is not even knowledge, though, that will be the reward. The goal is redundancy. It is the simple, practical, logical step of backing up the hard drive. Humanity is the data. Earth is the drive, and we have no backup. To have a second independent, self-sufficient human civilization on another world, whether it is Mars or a moon, is the single greatest insurance policy we could ever create for our species. If a catastrophe strikes Earth, be it natural or self-inflicted, the light of human consciousness will not go out, the story will not end. The art, the music, the science, the memory of Earth, it will all be preserved safe on another shore. And from that new shore, perhaps one day life could return to this world, to the cradle, to reseed the place where it all began. Leaving is not an abandonment of Earth. It is the only way to truly protect it. It is the only way to ensure that the dream of Earth continues. Earth is the cradle, but you cannot stay in the cradle forever. The universe is calling, and eventually, we must answer. We must learn to walk, and then to run, and then to fly, across the great dark distances, carrying our small precious light with us into the void. As humanity stands on the launchpad of a new interstellar age, we are forced to confront the reality that the greatest challenges are not technical but human. The equations for rocket propulsion are known. The physics of orbital mechanics are solved. But the physics of human nature, our tendency toward conflict, our difficulty with long-term planning, and the very definition of our identity remain the most complex variables. The true price of expansion is not measured in dollars or fuel, but in our ability to overcome ourselves. Before we can realistically dream of cities on Mars, we must first deal with the nightmare waiting just outside our front door. The space immediately surrounding Earth, specifically low Earth orbit LEO, is dangerously full. It is not full of satellites, but full of trash. This trash, known as orbital debris or space junk, consists of everything we have ever left behind. It includes dead satellites, the rocket stages that carried them, tiny flecks of paint chipped off by the harsh environment bolts, and even tools dropped by astronauts. There are millions of pieces of this debris ranging in size from a bus to a microscopic particle. The problem is not the amount of trash but the speed at which it travels. In LEO, objects move at astonishing velocities up to 28,000 km per hour or 8 km per second. At this speed, a fleck of paint has the same destructive kinetic energy as a bowling ball hitting a wall at highway speeds. A baseball-sized object has the impact energy of a small bomb. This sets the stage for a catastrophic theory known as the Kessler syndrome proposed by NASA scientist Donald J. Kessler in 1978. The syndrome describes a runaway chain reaction. Imagine one large dead satellite, Satellite A, orbiting the Earth. In a nearby orbit, another piece of junk B is on a collision course. They collide. The impact is not a gentle bump. It is a hypervelocity explosion that shatters both objects into thousands of new smaller pieces of shrapnel. Now, instead of 2 large objects, there are perhaps 10,000 smaller objects. Each of these 10,000 pieces is now a new bullet travelling at 28,000 km per hour. These new pieces spread out dramatically, increasing the statistical probability of hitting other things. So one of those new fragments, fragment C, hits a working active communication satellite, Satellite D. This new collision creates 5,000 more pieces of debris. These fragments hit other fragments. This is the chain reaction. Each collision creates a spray of shrapnel that in turn causes more collisions. The snowball gets bigger and bigger exponentially, increasing the amount of debris in orbit. If the Kessler syndrome reaches a critical point, low Earth orbit could become completely unusable for generations. It would be so filled with a cloud of high-speed shrapnel that any new satellite launch would be destroyed within minutes. The International Space Station would have to be abandoned. We would effectively be trapped on our own planet, surrounded by a cage of our own making, unable to get out. Our global systems that rely on satellites, GPS, weather forecasting, financial transactions, and global internet would collapse. This is not a distant theoretical problem. We have had warnings. In 2009, a non-functional Russian military satellite, Cosmos 2251, collided with an active American communications satellite, Iridium 30. This single event created over 2,000 new pieces of trackable debris and tens of thousands of smaller untrackable pieces. How do we clean it up? Cleaning orbit is one of the greatest engineering challenges of our time. It is incredibly difficult and expensive. You cannot just sweep it. You must actively go up and catch each major piece. Several ideas are being tested. The net. Some concepts involve launching a chaser satellite that deploys a massive lightweight net similar to a fishing net. It would capture a large piece of debris like a dead rocket stage, and then use its own thrusters to drag both itself and the junk down into the atmosphere, where they would safely burn up on re-entry. The harpoon. A more aggressive approach. The chaser satellite fires a harpoon into the debris. A strong tether connects the chaser to the harpoon, allowing it to reel the junk in, or more likely simply tug it into a lower decaying orbit. The laser. This is a more futuristic concept. A powerful ground-based laser or a space-based one would target a piece of debris. It would not vaporize it. Instead, it would heat one side of the object. This heating creates a tiny puff of outgassing from the object's surface, acting like a microthruster. By repeatedly nudging the object with the laser over time, we can slowly alter its orbit, pushing it down until it re-enters the atmosphere. Until these cleanup methods are viable, the only solution is prevention, designing all new satellites to automatically deorbit and burn up within 25 years of their mission ending. But this only stops the problem from getting worse. It does not fix the mess we have already made. The rules of the frontier, international cooperation. The second great challenge is political. Space does not care about borders. The laws of physics are the same over Beijing as they are over Washington. A piece of debris launched by one nation threatens the satellites of all nations. Humanity's expansion into space is not a journey for a single country. It is a multi-generational project for our entire species. Building a permanent base on the Moon or a city on Mars is a task of such immense cost complexity and duration that it dwarfs any single nation's budget or political attention span. These are generational goals. They require decades of sustained global cooperation. A president or prime minister serves for a few years. A Mars colony will take half a century to build. This requires a level of international trust and collaboration that we have rarely, if ever, achieved on Earth. We have a model, the International Space Station, which has been a stunning success in diplomacy, with former Cold War rivals working together peacefully in orbit. But this new era of expansion involving private companies and vast resources creates new friction. The biggest problem is the desperate need for space law. Our primary legal framework is the Outer Space Treaty of 1967. It was a product of the Cold War designed mainly to prevent nations from placing nuclear weapons in orbit. It states that space is the province of all mankind, and that no nation can claim sovereignty over the moon or a planet. But this treaty is dangerously outdated. It was written before anyone seriously considered private companies mining asteroids. It leaves the two biggest questions unanswered. 1. Who owns the resources? The 1967 treaty says you cannot own the moon. But can you own what you mine from the moon? If a private company spends billions of dollars to build a mining base on the moon and extracts helium-3, a potential clean fusion fuel, who does that resource belong to? Does it belong to the company that mined it? Does it belong to the nation that licensed the company, e.g. the United States via the Artemis Accords? Or as the 1967 treaty seems to imply, does it belong to all mankind, meaning the company must share its profits with the world? This is the single most likely source of conflict in the 21st century. If nations and corporations believe there is infinite wealth on the moon Mars, and in the asteroid belt they will fight over it just as they have fought over gold, oil and territory on Earth. 2. Who is responsible? The second question is about liability. The 1967 treaty says nations are responsible for the national activities in space, whether by government or private companies. What does this mean today? If a private satellite owned by SpaceX, a US company, malfunctions and crashes into the Chinese Tiangong space station, who's responsible? Is it SpaceX? Or is it the United States government which licensed SpaceX launch? What if the satellite was built in Europe, launched from New Zealand and insured by a company in Japan? Space law is a tangled mess of new questions. We must create a new binding international framework that governs resource extraction traffic control to avoid the Kessler syndrome and liability. If we fail to cooperate, space will not be a frontier of exploration. It will become the next battlefield. The human element, culture and identity. Perhaps the most profound challenge is not technological or legal, but philosophical and biological. As we leave Earth, the very definition of human will be tested. Who are we when we are no longer Earthlings? This challenge presents itself in two ways, one biological, one cultural. The biological challenge is what happens to our bodies. Humans are a product of Earth. We evolved over millions of years to thrive in this specific environment. A 1G standard gravity field, a thick nitrogen-oxygen atmosphere, and a powerful magnetic field that shields us from cosmic radiation. When we go to Mars, we are entering an environment that is deeply hostile to our biology. The radiation is higher, but most importantly, the gravity is different. Mars has only 38% of Earth's gravity. A person living their entire life on Mars would adapt. An adult who moves there will suffer. But a child born on Mars will be something new. For a child growing up in weak gravity, their bones would not need to be dense or strong, so they would likely develop chronic osteoporosis by Earth standards. Their muscles, including their heart, would not have to work as hard to pump blood uphill against gravity, so they would be weaker. Their spine might not be compressed, leading them to grow taller than their genetic code would suggest. These Martians would be a new, slender and fragile branch of humanity. They would be perfectly adapted to their new world, but they might be biological prisoners there. A Martian child might never be able to visit the home world of their ancestors. The crushing force of Earth's 1G gravity would be agony. Their weak bones might snap under their own weight. Their weak hearts might fail to pump blood to their brains. We would have, for the first time in history, two distinct human populations separated not just by distance but by biology. The cultural challenge is one of distance. How do you maintain a shared human culture when your neighbours are separated by millions of miles and a 20-minute time delay? A conversation between Earth and Mars is impossible. The speed of light is a hard limit. A simple hello from Earth would take on average 12 minutes to reach Mars. The reply hello would take another 12 minutes to come back. You cannot have a phone call, you cannot have a live debate. You can only send messages like futuristic video emails. Over time, this distance will inevitably lead to cultural drift. The colonists on Mars will have different priorities. Their lives will be defined by survival technology and the red dust of their new home. Earth's problems, our politics, our wars, our climate change will seem distant and abstract. They will develop their own slang, their own holidays like landing day, their own art and their own identity. They will be Martians first and humans second. How do we maintain a feeling of connection and shared destiny with a branch of our family that we can never visit, never talk to in real time, and who may be biologically different from us? This, however, is also our greatest opportunity. This is humanity's chance to start over. The Mars colony or the moon base will be a blank slate. It is a chance to build a new society from the ground up, designed with intention. It is an opportunity to leave behind the baggage of Earth's history, our ancient prejudices, our destructive nationalism, and our short-sighted economic models. Can we build a society on Mars based on the lessons we have learned? A society based on total recycling, scientific cooperation, and long-term sustainability? Or will we simply export our old problems, bringing our ancient hatreds and our capacity for self-destruction with us to the stars? This is the final test. The hardware is easy. The human heart is the real frontier. And so we drift. We have toured the architecture of the cosmos from the smallest grains of dust to the grand superclusters that stretch across the void like strands in a cosmic web. We have measured the light from the universe's dawn and calculated the slow cold fate that awaits it in the far future. We have seen that the universe is vast, ancient, and filled with the raw materials for life, which brings us at last to the most profound, most human, and perhaps most terrifying question of all. After all this searching, after all these numbers, these calculations, these epic journeys of the mind, are we alone? This question hangs in the air of every observatory on Earth. It is the silent companion to every astronomer peering through an eyepiece. It is the great unanswered riddle of our existence. It was summarized perfectly by the physicist Enrico Fermi during a casual lunch conversation. He looked at the mind-bending numbers, hundreds of billions of stars in our galaxy alone, billions of galaxies in the visible universe. He considered the age of the cosmos 13.8 billion years, plenty of time for life to arise and evolve. He knew the building blocks of life, carbon, hydrogen, oxygen, are forged in the hearts of stars and scattered across space. Given all of this, he argued the universe should be teeming with life. It should be noisy. Civilizations far older and more advanced than ours should have risen, mastered interstellar travel, and spread across the galaxy. Even moving at slow sublight speeds, a civilization could colonize the entire Milky Way in just a few million years. On a cosmic timescale that is the blink of an eye. They shouldn't have left signals. They should have built structures we could see. They should, by all statistical logic, be everywhere. And so Fermi asked his simple, devastating question: where is everybody? This is the Fermi paradox. And it is deepened by the profound, deafening, eerie silence we have found so far. We have turned our most sensitive instruments toward the sky. We have built massive radio dishes nestled in quiet valleys, listening for the faintest whisper of an artificial signal. A beacon, a greeting, or even just the stray traffic of a distant alien world. And we hear nothing. We hear the hiss of the ancient radiation left over from the Big Bang. We hear the rhythmic pulse of dying stars, the neutron stars that spin hundreds of times a second. We hear the roar of supermassive black holes devouring matter at the hearts of distant galaxies. The universe is full of natural noise, but of intelligence, of purpose, there is only silence. We have scanned the nearby stars for the chemical fingerprints of industrial pollution in their atmospheres. We find nothing. We have looked for megastructures, hypothetical engineering projects on a stellar scale like spheres built around stars to capture all their energy. We see no such thing. The silence is the single most important piece of data we have. It suggests that something is wrong with our logic. Either life is incredibly rare, or intelligence is rare, or the lifetime of a technological civilization is tragically short. This leads us to a chilling concept known as the Great Filter. The Great Filter is a hypothesis that attempts to solve the Fermi paradox. It suggests that on the long evolutionary path from simple matter to a galaxy-spanning civilization, there exists some barrier, some filter that is almost impossible to overcome. It is a challenge so difficult that it stops virtually all life in the universe from ever reaching the stage where we could detect it. The terrifying question for humanity is not if the filter exists, but where it is in our timeline. There are two main possibilities. The first possibility is that the Great Filter is behind us. Perhaps we are the first to have passed it. Perhaps we are the only ones. This is the rare Earth hypothesis. Maybe the filter was the initial spark of life itself, the leap from non-living chemistry to a self-replicating cell. Maybe this event is so statistically impossible that it only happened once here on this small wet planet. Or perhaps the filter was the jump from a simple cell to a complex one, a process that took nearly 2 billion years on Earth. Or perhaps it was the evolution of a brain capable of abstract thought language and tool-making. If the filter is behind us, then the universe is sentient because we are quite simply the first. We have won the cosmic lottery. The silence is not a graveyard. It is an empty, untouched garden, waiting. It means the galaxy is ours for the taking, an open frontier for our descendants. It is a lonely thought, but also a hopeful one. But then there is the second, much darker possibility. What if the Great Filter is ahead of us? This possibility suggests that life and intelligence are common. The universe in this scenario is full of budding civilizations, full of creatures who, like us, looked up at their stars and began to build, to communicate, and to dream. But in this scenario, there is a trap that every technological civilization inevitably falls into. Perhaps it is technology itself. Perhaps every civilization discovers the power of the atom, but inevitably uses it to destroy itself in nuclear fire. Perhaps every civilization develops advanced artificial intelligence which then surpasses and eliminates its creators. Perhaps it is a climate-related collapse, an ecological point of no return that no one can manage. Or perhaps it is some scientific discovery we have not yet made, a physics experiment that goes wrong and sterilizes a planet. If the filter is ahead of us, then the great silence is not an empty garden, it is a graveyard. The silence is the sound of countless civilizations that reach the exact same point we are at now, and failed to pass. The silence is a warning. It is the collected ghosts of a billion worlds whispering, "Be careful, we did not make it." This uncertainty places us in a unique and profound position. Let us, for the sake of our own future, consider the implications of the first scenario. Let us assume we are the first, that we are alone. What does this mean for us? If we are the only spark of consciousness in the Milky Way, or perhaps the entire visible universe, then our existence is the most precious and significant thing that has ever happened. For 13.8 billion years, the cosmos has been a grand, beautiful, but unthinking machine. Stars burned, planets spun, galaxies collided. There was light, heat, and matter. But there was no awe. There was no beauty. There was no understanding. The universe existed, but it did not know it existed. And then, on this tiny mote of dust orbiting an average star, the universe woke up. We are the part of the cosmos that became self-aware. We are the universe's way of looking at itself. The atoms in our brains, forged in the hearts of long-dead stars, have now assembled themselves into patterns that can comprehend the stars they came from. This consciousness, your consciousness right now, listening to these words, feeling the slow rhythm of your breathing as the universe's spark, we are the ones who can feel love, ask why, create art, and search for truth. If we are the only ones, we carry an immense responsibility. We are the sole custodians of this spark. We are the keepers of meaning. If we allow this flame to go out through war or negligence or accident, then the universe will fall silent again. The cosmos will revert to being a magnificent but empty machine. All the beauty of 1,000 spiral galaxies will exist with no one to see it. All the laws of physics will operate with no one to marvel at them. If we are the only spark, we have a sacred duty to preserve it. Staying on one planet, therefore, is an unacceptable risk. It is placing all of meaning in one fragile basket. A single rogue asteroid, a massive solar flare, a self-inflicted catastrophe, and the spark is gone forever. This changes the entire narrative of space exploration. The expansion of life beyond Earth is no longer just about survival or resources, or even the thrill of discovery. It becomes a moral obligation. We have a duty to safeguard this flicker of awareness. We must make copies of it. We must carry this light to other worlds, to Mars, to the moons of Jupiter and Saturn, and eventually to other star systems. We must spread out planting seeds of consciousness across the galaxy to ensure that no single event can extinguish it. We must become a multiplanetary and then an interstellar species, not because it is our destiny, but because it is our responsibility. This brings us back to the ultimate why. Why do we look up? Why do we dream of travelling to the stars? The old answer famously given about climbing a mountain was, because it is there. But that is not enough. The universe is just there. A rock is just there. They are magnificent, but they are passive. We, however, are not. We do not go to the stars simply because they are there. We go because we are here. We go because we can make it matter. By going, we bring meaning to the void. We bring awareness to the silence. We carry the spark of the universe back to the stars from which it was born. We are the custodians of meaning, and it is our purpose to carry that small, precious human light into the great silent and waiting darkness. And as you drift off to sleep, hold on to that thought. You are not just a person in a room on a planet. You are the universe's way of knowing itself. And in your dreams, you are the astronaut, the pioneer, the keeper of the flame. Even if we achieve it all, if humanity or its descendants conquer disease, master interstellar travel, and unlock the deeper secrets of the quantum world, We cannot escape the final absolute limitation. We can overcome our biology, our planet, and even the dangers of our own galaxy, but we cannot overcome the universe itself. The cosmos has a lifespan, and the laws of physics have already signed its death warrant. The first hint of this end is not a cataclysm or a collapse, but an acceleration. For a long time, we believed the universe was in tug of war. Gravity, the force that pulls everything together, was battling the outward momentum of the Big Bang. We wondered which would win. Would gravity pull everything back into a big crunch or a fiery rebirth, or would the expansion just slow down forever, fading gently? The answer we discovered was neither. The expansion of the universe is not slowing down, it is speeding up. There is a mysterious force at work, something we have named dark energy. We cannot see it, we cannot touch it, and we do not know what it is, but we see its effect everywhere. It acts as a kind of cosmic anti-gravity bolted into the fabric of space itself. While gravity pulls matter together, dark energy pushes space apart. And unlike gravity, which gets weaker with distance, dark energy's push is constant. As more space is created, the total push gets stronger. This has a profound and terrifying consequence for the very distant future. This relentless, accelerating expansion means that galaxies are not just drifting away from us, they are speeding away from us. First, the most distant galaxies will be pushed away so fast that their light is redshifted into oblivion, stretching until the wavelengths are too long to detect. Then something even more profound happens. The space between us and those distant galaxies will begin to stretch faster than the speed of light. This does not violate Einstein's laws. Nothing is traveling through space faster than light. Rather, the space itself is being created between us so quickly that light from those galaxies can no longer cross the gap to reach us, no matter how much time passes. They will be ripped from our observable universe forever. One by one, like lights going out in a distant city galaxy clusters, will cross this cosmic horizon and vanish from our sky. The universe will become an increasingly lonely place. Our own local group of galaxies, including the Milky Way and Andromeda, will merge into one enormous supergalaxy. But everything outside this gravitationally bound island will be gone, lost forever in an expanding empty void. The night sky, once glittering with countless points of light, will become almost completely black. We will be alone. But the end does not stop there. Isolation is only the beginning of the true decline. The universe is governed by a fundamental law, the second law of thermodynamics. This is the law of entropy. Entropy, in simple terms, is the rule that everything in the universe tends toward disorder. A hot cup of coffee always cools down, spreading its heat into the room. A structured sandcastle is always washed away by the tide. Energy always flows from a concentrated, useful state to a spread-out, useless state. This law is the arrow of time. It is why things decay, why things break, and why things die. For eons, our isolated supergalaxy will still be alive. Stars will burn, but they are burning a finite amount of fuel. The great bright blue stars will die first in massive supernova explosions. Then the yellow stars, like our sun, will swell into red giants and collapse into white dwarfs. The longest lasting stars, the dim red dwarfs, will sip their hydrogen fuel for trillions of years, but eventually they too will go cold. The universe will enter its degenerate era. The age of stars will be over. All that will remain are the corpses of stars, coal black dwarfs, dead neutron stars, and black holes. For a time that is almost impossible to imagine, these black holes will be the only organized things left in the cosmos. They will be the last guardians of order, swirling gravitational titans in an otherwise dark and empty void. But even they are not forever. Entropy always wins. The physicist Stephen Hawking discovered that black holes are not truly black. Due to strange quantum effects at their edge, they very, very slowly leak radiation back into the void. This process, known as Hawking radiation, means that black holes evaporate. The process is unthinkably slow. A black hole the mass of our sun would take 10 to the power of 67 years to evaporate a 1, followed by set zeros. The supermassive black holes at the centers of galaxies will take a Google years, a 1 followed by 100 zeros. This number is so large that if you tried to write it down, the ink required would have more atoms than all the atoms currently in the universe. But the universe has nothing but time. Slowly, agonizingly, the last black holes will hiss away into nothingness. When the last black hole evaporates, the final bit of structured matter in the universe will be gone. This is the heat death. It is not a death of fire, but of ice. The universe will become a vast, dark, and unimaginably cold place. It will be nothing but a thin uniform soup of stray particles, photons with wavelengths trillions of light years long, lonely electrons and the neutrinos drifting eternally apart in an ever-expanding darkness. The temperature will approach absolute zero, negative 273.15 degrees Celsius or 0 Kelvin. When the universe reaches this state of maximum entropy, no more work can be done. The difference between hot and cold, which drives all energy and all life, will be gone. There can be no more structure, no more information, no more complexity, no more thought, no more life. Nothing lasts forever. Entropy always wins. So what is the point? If this is the inevitable end, a cold, empty, meaningless void, why do we struggle? Why do we build civilizations? Create art, fall in love and search for knowledge. If it all just fades to black, what is the meaning of our existence? This is the final philosophical challenge. The universe does not promise us a happy ending. It does not promise us meaning. But perhaps we are looking at it the wrong way. Maybe survival is not about beating death, but about defying it. Life itself is an act of defiance. Entropy is the law that says decay and disorder. Life is the phenomenon that says build and organize. We are temporary fragile islands of complexity in a cosmic ocean that pulls everything towards simplicity. We are the universe becoming aware of itself, even if just for a fleeting moment. The meaning of our struggle is not found in the final outcome which we cannot change. The meaning is found in the struggle itself. The value of life is not measured by its duration, but by its depth, by its capacity for experience, for knowledge, and for compassion. We cannot stop the night from coming, but we can build a fire. We can leave echoes. We can leave traces in the fabric of time. Even if every structure we build turns to dust, and even if the last black hole evaporates, the universe will be different because we were in it. We imposed meaning onto a universe that had none. We loved in a cosmos that was cold and indifferent. Our ultimate purpose then is not to live forever. It is to live now and to pass a torch of consciousness and memory forward. It is to leave a mark, a story rewritten into the stars, a final testament that says, we were here, we understood, and we tried. Not in a ship of metal and fire, but in our minds. Go back there just for a moment and stand on that quiet grey dust. Look up. You will see something incredible. You will see a bright, marbled, perfect blue and white sphere hanging in the absolute black. You will see home. You will see the Earth. It is strange perhaps to end our vast journey through the cosmos by coming back to something so close. But the moon is our mirror. It is the faithful watcher that has seen our entire story. It saw the first single-celled life. It saw the dinosaurs. It saw the first humans look up and wonder what that light in the sky could possibly be. And when we finally found a way to leave our world to build the incredible machines of escape, what did we bring with us? It is the strangest, most beautiful paradox of our species. Amidst all the technology, the computers calculating orbits, the engines burning hydrogen, the suits protecting us from the hard vacuum, we still carry the most ancient things. We do not go into space alone. We carry our stories with us. We carry our myths. We carry our art and our music. When the first humans stepped on the moon, they did not just collect rocks. They planted a flag, a symbol which is a form of storytelling. They read poetry. They left a plaque that spoke of peace for all humankind. We cannot help it. It is what we are. After all this time, after all the equations and the discoveries, the awe is still there. The wonder has not faded. If anything, it has grown deeper. To know that the star you see is not just a point of light, but a giant fusion reactor, burning for billions of years, is more wondrous. To know that the universe is expanding, that we are all made from the dust of stars that lived and died long ago, this knowledge does not make the universe cold. It makes it personal. It makes us part of a story so vast it is almost impossible to comprehend. This feeling, this catch in your throat when you see a galaxy swirling in an image from a telescope, this sense of being small but also connected to everything, that is awe. And that awe is the engine of our exploration. It is the fuel that is more powerful than any rocket. We search the skies for answers, but perhaps our greatest gift is not in finding answers, but in creating them. The universe by itself simply is. It expands, stars are born, and stars die. It is a grand, silent, beautiful performance, but it does not have a meaning not until a consciousness wakes up to observe it. We are that consciousness. We are the part of the universe that woke up. And our gift, our true, unique human gift, is the ability to create meaning. We look at the silent, empty void and we fill it with stories. We connect the random dots of stars and we create constellations drawing pictures of our heroes and our gods in the dark. We take the cold data from a distant probe and we turn it into a song. We look at the silence and we invent music. This is what we do. We are the meaning makers. and so we will carry this to the star. If we ever travel to Mars or to the moons of Jupiter, or even one day to a new solar system, we will not just be bringing our science and our machines. We will be bringing our humanity. We will bring poetry to the stars. We will stand on a new world under a new sky, and we will do what we have always done. We will tell stories about it. We will paint it. We will write poems about the strange colour of its sunset. We will try to find our place in it. The final mission you see is not what we think it is. We often talk about space as an escape. We talk about escaping gravity, escaping the problems of Earth, escaping our own limitations. But the journey has never been about escape. It has been about understanding. The ultimate purpose of pushing outward is not to leave our home behind, but to finally see it and ourselves for what we truly are. The ultimate mission is not to escape gravity, but to make the journey meaningful. And so our own journey for tonight comes to a close. As you lie here ready for sleep, feel the gentle, steady pull of gravity. It is not a prison. It is an anchor. It is the planet holding you, keeping you safe. It is the Earth, our silent, spinning ship carrying us through the vast, quiet night. Think of that ship. It is carrying its precious cargo. It is carrying all the stories ever told and all the songs ever sung. It is carrying all the art and all the love and all the dreams of 7 billion people. And it is carrying you. You the dreamer. You the storyteller. You the small, wonderful part of the cosmos that woke up to feel awe. Let the great, dark silence of space not be frightening. Let it be a blanket. Let it be a peace that settles over you. Your journey tonight into sleep is its own kind of exploration. It is a journey into rest, into renewal, into the quiet inner space where your own meanings are made. The stars will keep watch, the moon will continue its ancient silent orbit, and you can rest. Sleep well and carry your own quiet poetry into the night.